Hello folks. In machining there are many factors that contribute to tool breakage, excessive tool wear, scrap parts, and things like that. In this particular episode I'd like to talk about what we call spindle wear. Now I've drawn a spindle up here of a particular machine, and it's meant to represent a Morse taper. Morse tapers were invented somewhere back in the 1860s, so they've been around for a long time. And a lot of machines use them and for a lot of different things. In this application here, I'm particularly talking about a drill press with using twist drills, because that's a fairly common thing and a lot of shops have it. Now, the important thing with something like this is to know your machine. You know, if it's over 20 years old, you're going to have problems with it, and that's just the way it is. It comes with normal use. But also, if you don't know the history of this machine, that can be a very significant factor, because you don't know what it's been up against in the past. You don't know if people have really abused it badly, or if it's been well taken care of. Unless you have a lot of records on it, which a lot of times as used equipment, you don't get those records. Anyhow, in this case here, I want to talk about spindle wear. This here is my representation of a Morse taper in a spindle. It's not exactly dimensionally correct, but it ought to be close enough. And I made myself a little model of a twist drill with a corresponding Morse taper on it. Now, under normal use, these tools like this will be just kind of slapped up inside there, and it holds them. This is what we call a locking taper. A Morse taper is a very slight angle, and it actually locks inside there, and it gives it enough surface area to grip it and push it through the metal that it's cutting without slipping. The tang, that's what we call this portion up here at the top. It's actually a flap that goes across there, but it's radiused on the sides like that. It is not meant to drive the tool. All the driving is meant to be done by the interface between the two mating tapers there. That is a locking taper. The tang is just there so you can put a tool through a wedge through a slot in the spindle and pop it out. You just tap and the drill comes out. That's what that's for. Now, occasionally the tang does do a little bit of driving, but under normal circumstances, it's not meant to drive your tool. It's only there for removing the tool. Okay, all the driving is done by this. Now, if you have a problem with your tools either not going in there when they stay in there, or staying in there when you put them in there, or falling out prematurely, if you have problems with tool breakage or excessive chatter, those could be caused by excessive tool wear inside the taper here. And how does that happen? Well, ordinarily, a taper like this, before it's put in, taper on any tool, whether it's a drill or an end mill or a boring head or whatever you have, when it's put inside there, this should always be wiped clean. Blowing it clean is not good enough with an air gun or something like that. You've got to wipe it clean. Make it nice and clean. Correspondingly, this has to be clean inside here too. Now, I'll take a rag and wrap up some piece of tooling or something, a rod or whatever, and with the machine off, shut off. Make sure it's switched off so you can't accidentally turn it on. You take that and you put it up inside there, and you twist it and you wipe it around there to clean that out. Blowing it with an air gun isn't good enough usually. You've got to get the actual dirt out. You want to get the grease out, the oil, and whatever's sticking in there. And same thing with this here. You wipe it with a rag. Now, here's another thing a lot of people don't think about. They take these tools and they bang them around all over the shop. They drop them on the metal tables, they drop them on other tools, they drop them on the floor, they drop them all over the place. No big deal, just put it in there, let's go. Well, those get dings on it, and those dings will actually begin to wear out inside here as well, because they go up there and they're jammed in there, and they start making impressions in the mating surface there. That is not good. Whenever you have metal tools and you use them, set them down on something like cardboard, a rag, a piece of wood. Don't set them down metal to metal. That will ding them, makes them dull, makes them worn out, it's just not a good practice. Okay, with that in mind, you've got a machine here that's maybe 20 years old, maybe 50 years old, whatever. You've got thousands of tools being popped in and out over the years like this. What's going to happen to that spindle taper? Over a period of time, this will get worn too, but especially this, because it's there day in and day out, and it's got thousands of tools going in and out of it during the course of its lifespan. And what you're going to get is a certain wear pattern. Look at what happens here. When you take this taper here and insert it there, what part of the drill and what part of the spindle are contacting each other first? Well, it's going to be this area on your tool and this area right here on your spindle. That's where it's going to contact the first. When it goes in there, where is it going to contact the least? Up here. Beep, beep. Just a little bit of contact up there. Most of the contact happens down here. So what does that mean? That means as you slide this tool in and out, if you put it straight up like that, like most guys don't, if you put it straight in like that, you minimize the wear on your spindle. But if you put it in at an angle and just bang it in there, you're going to get a wear pattern to exaggerate just a little bit. That's going to look something like this. It's going to be bell-mouthed. Okay? Now if you put a nice straight tool in like that, nice clean taper, and it's bell-mouthed like that after 20, 30, 40 years of use, where do you think the gripping is going to take place? Right up here in this area, it's going to grip along that where it's least worn, and that's about the only place it's going to grip. Down here, depending on how bad the wear is, it's not going to grip so much. What does that mean? That means that when you put your tool in there and it's held up there, it's like, hey, yay, it's good, it's staying put this time. Yes, it is, but that means it can chuckle back and forth like this. And that is going to cause your tool to break. So that's not a good idea. You want to take care of this. Now, if your spindle is worn like this, you got to get a new machine. There's not much else you can do about it. You could have a company take this apart and regrind it, possibly plate it up and then put in a taper, regrind a taper in there right to size, but that's expensive. And generally speaking, that's throwing good money after bad, because if this is worn out like that, chances are real good that there's a lot of other things on your machine that are correspondingly as bad condition as that is. So you might fix this and it's like, yay, now it holds my tools, but there's other things that are wrong with the machine, and it's not going to perform quite as well as you'd like it to. Now, there are a couple things we can do to check this and see if this is really the problem or not, because it may not be. You may have a machine that's been well taken care of and that's not an issue. What you can do is you can take this, a good tool with preferably something like an arbor for a shell mill or something like that that's got a straight diameter on it here, and you pop that up in there and you can put a test indicator on here. Now I don't have one to show you and I'm not going to try to draw a picture of that, but you put a test indicator on here, and with the spindle in neutral, again the machine off, but the spindle in neutral, you can rotate your spindle and see if this actually wobbles out like that. If it runs eccentric, then you know you've got problems up here in your taper. Well, so long as you've got a good tool going in there. If this thing here is a piece of junk, if it was not manufactured well, then it's probably going to run out anyhow, and it'll give you a false idea of your condition. But here's another thing you can do. With your indicator on this side, let me draw a little indicator. Here's an indicator. It's got a little needle on it, all these little graduations going around. It's got a little probe that comes out like that, let's say, and you've got it up against your tool like that. If you wiggle it back and forth, put your hand on this and try to push that back and forth and see if that goes, and that indicator will show if there's movement there. Okay? Now, it might resist that and not show you because you're not Mr. Hercules here. So you could tap it with a hammer, go bink, 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 and see how easily it moves. That would be an indication too. But there is one other thing, and that is that a lot of times you won't get any indication that there's a problem here until the tool hits the metal and you're actually making a cut. Then under the force of cutting metal, this thing begins to walk around and do its thing. And so it can be kind of hard to find, a little tricky. Okay, now that's with the indicator. There is one other little trick you can do, and that is to buy a piece of tooling, or make sure you've got a piece of tooling where it's got a real nice clean taper in pristine condition, okay, but no tang on it. And you can get things like that, or you can take a tool that's in, where it's all busted up here, but the taper is still good, and machine that off. What you want is a straight cone here with no tang on it. And you get a tube of this material. It's called Prussian blue. It's Prussian blue. You get some Prussian blue, and it's like an oil paint. And what you do is you squirt that onto your finger, onto the thing, onto your taper here, and you smear it as evenly as you can, all the way around. Smear it nice and round, you know, spin it around, get it on there as evenly as you can. Tool and die makers used to do this. I don't know if they still do anymore, but they at least used to. You smear Prussian blue, it's like an oil paint. You smear it on there as evenly as you can, all the way around. You stick it up in your spindle there that you've already cleaned, and you rotate that thing back and forth just a little bit, just like 30 degrees, 30 degrees, 30 degrees, just like that, while you're holding it up inside there. Then you pop it out and you look at it, and wherever the Prussian blue is rubbed off is where it's making contact in the spindle. And what you'd like to see is a uniform smearing all the way around, from top to bottom, all the way around. That indicates that you've got a well conditioned spindle there, and that your taper is also in good condition. If it isn't, if you see little rings on there, little scrape marks that are very silvery and where it's pushed away the Prussian blue, then you know that's where it's making contact, and it's not making contact wherever the blue is still on there. Okay? All right, well, that's it for today. Thank you very much. God bless you.